I completely avoided talking about the CFT description and their viewing the tau function as a conformal block. So maybe you're thinking in that direction?
Yeah, may I perhaps at this point offer like 2 sentences? The point is these theta series expansion actually can be seen as a kind of transformation mapping you from something which is generally quantum in terms of monodromy data and quantum character variety. That is sort of the right-hand side to what is becoming classical thanks to some fortunate accident on the left-hand side, which is the tau function world. But I'd be happy to, or Joanna can say more about this maybe later.
Yeah, maybe later.
So I think we should start, getting ready for Simon's second lecture.
Simon, do you want to share your screen to check that that's working? You should. There you go. Right.
Oh, great. Okay, so that's easy.
Okay, so it's 12:30 now. Should I go ahead and mute everybody and then Simon and Miriam unmute themselves and then go? Okay.
Okay.
Okay, I've muted everyone. So.
Okay. So we are ready for the second lecture today and for the second lecture of Simon on the deformations of singular sets and Nash-Moser theory. Please, Simon, go ahead.
Thank you. So just to review, recall we're interested in these, the setup with what we call a branched maximal section over a manifold M, which is a solution of a second order PDE with a certain kind of singular behavior over a codimension 2 subset sigma. And the result we're focusing on is a deformation theory for these objects. And as I explained in the second part of the talk, these are of interest from the point of view of special holonomy and related at least distantly to other topics in this workshop when we consider higher dimensional manifolds fibered over our manifold M, and this set, singular set sigma, appears as what you might call the discriminant locus, over which the fibers become singular. Perhaps what I didn't say explicitly yesterday, but maybe should make clear, is that the bundles that appear, for example, a bundle with this fibers, these vector spaces with an indefinite quadratic form, these appear as the cohomology along the fibers of our manifolds Z, of our map from Z down to M. So roughly, we're replacing the whole complicated manifold just by the base space and this sort of cohomology data of the flat bundle we get from the cohomology along the fibers. So that's just the review. Let's begin the main part of today's talk. Well, I want to say something about the proof of this kind of deformation result. And as in the title, this involves a piece of technology and analysis called the Nash-Moser theory, which I should say I'm a very long way from being an expert on, but we'll give a short indication of the main ideas. So this is a sketch following this helpful paper of Saint-Raymond, which gives a kind of a simple version of this main Nash-Moser theorem. So the situation is we work in what are called Frechet spaces. So these are things with a collection of norms of increasing strength. So the basic example would be to think of smooth functions with the CK norms, or we could use some Sobolev norms or Hölder norms. Though all of these would actually be equivalent in the sense that by the usual embedding theorems are given, if you go sufficiently high, the CK norm is controlled by a suitable Sobolev norm, for example. And then the other piece of structure we need are smoothing operators acting on, in fact, as one of the spaces on V, the parameter epsilon, which have the property that they improve the smoothness. So if you take a positive number R, then we control the K plus R norm of the smoothed object. If we apply this smoothing operator to U in terms of the K norm, but the factor is gets worse as this parameter epsilon decreases. But also, we need that these smoothing operators are approximations to the identity as epsilon goes to 0. So again, in the case of, say, functions on R, then you would get this kind of operators in the standard way by taking convolution with a some suitably family of bump functions scaled according to this factor epsilon. Or you could think about it in terms of Fourier series, that we define the operator by removing or reducing the high Fourier series terms, or high part of the Fourier transform. There's also another more technical condition that these norms should satisfy certain interpolation inequalities, which again are standard things in the case of these kind of function spaces. So then the setup we'll consider is we have an open subset in one of our Frechet spaces, V, and a map from U to the other one. So this could be given by a differential operator, for example, satisfying certain kind of natural estimates of bounds on F in terms of these norms, and also on the first and second derivatives of F. And the crucial hypothesis is that we could invert the linearization of this map F. So at each point in U, we have the derivative of F, or the corresponding linear operator, and we want there to be for the result, the path of the result, we'll consider just a right inverse QU to this. So if I take the composite of the derivative of F with Q, I get the identity on V, and we want this to satisfy bounds in terms of our scales of norms, but essentially the Q of sigma, the norm of the kth norm of Q of sigma is controlled in terms of the K plus dth norm of sigma for some suitable D. Plus an extra term which gives you some freedom as the point U varies around. Then the statement is that if we have one solution of the equation f of u equals 0 for some particular u naught, then if I take a row sufficiently close to 0 in our space W, then we can solve the equation f of u equal to rho. There's a kind of an inverse function theorem that says that the f maps onto an open set in W. We're just focusing on the existence part of the discussion here. If we also had the condition on the left invertibility of this derivative, then we get sort of uniqueness statements. So this is in shape a familiar kind of inverse function theorem, going from hypothesis on the derivative of a map to a hypothesis about the map. Okay. But let's go back. But the point is, if we compare it to the more elementary kind of implicit function theorem in Banach spaces, in other words, if you were working in the suitable, say, CK spaces or Holder spaces or Sobolev spaces for some fixed value of K, the point here is that the inverse Q is allowed to lose a fixed number of derivatives. For example, supposing our f is given by, say, a second order differential operator, some kind of nonlinear second order differential operator, then if we are working in Banach spaces, we could have a similar kind of result, provided our inverse gained us two derivatives. It would need to map from, roughly speaking, functions with R derivatives to functions with R plus 2 derivatives. The point of the Nash-Moser theory is you don't need to care about exactly what number of derivatives you have, provided you only lose some fixed amount. Now the proof, it involves, essentially, we can write down more or less Newton's method, Newton's approximation scheme that we would use to solve this equation by, at each time we change, we modify our approximation by using the inverse that we have. But the essential feature is that we introduce smoothings into that procedure by taking the parameter epsilon to be chosen suitably. So the convergence is fast enough that you can change things by a little bit by doing this smoothing to gain more derivatives, but you don't lose the convergence of the solution. So actually, to go backwards, what we need is slightly different. In fact, one could put it in the previous format if one wanted, but we'll think of it slightly differently. Supposing our f is f0 is one of some family of such maps, for example, parameterized by just some finite dimensional parameter t, then and satisfying the suitable kind of extension of the hypotheses we had to this family, then if we have a zero of the original map, f0, then we can find zeros of this family. We can find a smooth family of solutions of the equation ft of u equal to 0. And yeah. So that's the sort of foundational theory that we want to fit into. So now we want to discuss sort of how to do that. And this has two aspects. One is the sort of differential metric, how to set things up appropriately. And the other is more analytic, involving function spaces and estimates and so forth. So to begin with, oh, do I see a question? Did I see a question? No. Okay. So to begin with the sort of differential metric setup, let's first review what one does if we didn't have to worry about the singular set sigma. So we're imagining that in the case when sigma is empty. In reality, for the particular problem we're discussing, that will hardly ever happen in an interesting way, but let's think of it anyway. So remember that the hypothesis is that the derivative of h naught should define using the flat structure, it should define a injection into the fiber. So actually, I forgot to say something. For simplicity, we will just discuss the codimension 1 case when m is 1. See, really, we're mainly interested in the case when m is 19. It doesn't matter what m is. Taking difference of values of m makes some complications in the setup, but not really of an essential kind. So we'll, to simplicity of exposition, we'll look at this case when m is 1. So our hypothesis is that the derivative of our section maps into a codimension 1 vector subspace in the fiber, so we can take its orthogonal complement, which will be just give us a line subbundle, nu. So then we would consider varying our section by adding on a section f of this line subbundle. So locally, when we're representing everything just in terms of submanifolds inside our space, this is just the completely standard thing, but you vary your codimension 1 submanifold by essentially a function giving the motion in the normal direction. Then the equation we want to solve is the vanishing of the mean curvature. This is always normal to any submanifold. So if f is sufficiently small, it is uniquely determined by its projection to this the original normal, nu. So we define curly f of f to be given by the projection of the mean curvature of the nu section to the direction nu. So we have our map, our nonlinear map, curly f. It maps from sections of nu, but only sufficiently small ones, because we want to preserve this maximal condition, for example. But it maps, the image is given again by a section of nu. And this is, I say, completely standard. The derivative at 0 is again a familiar thing. It essentially corresponds to what's called the second variation formula in minimal or maximal submanifold theory. And it's given by the following. It's given by taking the covariant Laplacian, which actually here essentially is the Laplacian, because we just have this, well, that's right, it's not quite true. This is this, yes, so nu is a line bundle, so it's locally it's trivial, and this is just essentially the ordinary Laplace operator, and then we have a term involving the geometry of our submanifold. If we worked in the Euclidean situation, then we would have a minus sign here. This is S is the second fundamental form of our section. In the Euclidean situation, we would get minus the norm of S squared times F. In other words, what that means is that in the Euclidean situation, the more the submanifold twists and turns, that has a tendency to make the second variation negative. It tends to make your minimal surface or submanifold unstable. But in this indefinite case, the signs change, and so we get a positive term here. So this whole thing is a positive operator, and by standard usual elliptic theory, that means that we can invert it on usual function spaces. The fact that we get this different sign is an example of a sort of general phenomena that this maximal submanifold equation is in many ways better behaved than the minimal submanifold equation. All the signs tend to work out in a favorable direction. So let's explain this. Well, that's a bit hard. So if we work locally around sigma, then we have this subbundle of our bundle given by the reflection. So if we take a loop going around sigma, that defines this reflection, which picks out a one-dimensional subbundle of our given bundle. And we can take the complementary one, say E plus. So we can write our bundle naturally on a neighbor to sigma as a product over n. So we'll choose, we can begin to choose our subbundle nu, the general situation, to be given by this, as it were, fixed one-dimensional subbundle E minus near omega, and by the normal construction as above, away from omega. And then we can smoothly interpolate between those in some obvious way. So now let's, for simplicity, let's suppose that this flat bundle E plus is actually trivial over this open set, and we fix the trivialization. So the fibers of E plus have a fixed identification with Rn. Then our hypothesis means that we can identify a neighborhood of sigma in M with some open set in Rm, and so sigma corresponds to some submanifold S inside this open set. And then we have, slightly abusing notation, we have our flat line bundle, which you can think of as defined over the complement of S in Rn. So under this identification, our section, our submanifold is written as a graph. So our section S in the E plus component, it's just given by the identity map. And then we have a more or less a function, or precisely a section of this line bundle E minus, say U0, which gives the interesting information. So what we're doing is we're saying near to sigma, we can essentially describe things in the way we did in the last lecture when we wrote down the maximal submanifold equation for a graph. Let's just, this is a bit, let's, what do we do? See if we can, okay. So this is a picture to explain this. So it's a bit confusing. So remember we said that sigma itself inside M is not really an intrinsic geometric thing. The diffeomorphisms of Mx, and we could map sigma to any other nearby submanifold. But in this setting, the submanifold S in Rn is really an intrinsic geometric object. Geometry of S is something intrinsically attached to our original solution. But under this hypothesis of the triviality of our bundle, which is not really a serious hypothesis, it just makes the notation simpler, we can when we're discussing what's going on near to sigma, we can really work as though we can work in this open set in Rn as described. let's pick up. But now that's before we do any variation. Now, if we take a diffeomorphism from omega prime to omega prime, compactly supported and so small and so close to the identity, and supposing we have some section of this bundle, E minus, over this bundle with this fixed singular set S, then we can define a new section by the following, that in the horizontal direction, we move by psi of x, and then we change our component in the vertical direction by adding on f. We also want to make some assumption, more technical, on the derivative of psi in the normal direction on S. We want the derivative of psi to isometry acting on the normal bundle of S. So what this means is that we parameterize variations of our section by pairs of f and psi, where psi is a diffeomorphism of a neighborhood of S in omega primed, but we could equally, under identifications, think of that as a diffeomorphism of a neighborhood of sigma, if we wanted, and f is a section of the line bundle nu. So near to sigma, we're making this construction. Away from sigma, we're making the normal variation construction as we considered before. So this is a picture of our diffeomorphism that we're considering can move S to some nearby submanifold. So now we'll define a curly f of these two variables, psi and f, to be the projection of the mean curvature of this new section that we've discussed to our bundle nu, evaluated at the point psi of x. So this is a bit confusing, or at least I find it quite confusing. What's going on? Near to sigma, we can use this identification to work in this identification with a neighborhood of sigma with a neighborhood in R of n to work in standard flat coordinates, the standard coordinates in Rn. And then we can write our equation f is written as Laplacian with respect to g of u, where u is given by modifying our original function by adding on f. And the Laplacian is taken using the Riemannian metric, which is given by this. We pull back the Euclidean metric on Rn by this diffeomorphism psi, and then we add the contribution from the vertical direction. So these psi I and psi j denote the derivatives of, so psi I and ui represent the derivatives of psi and u. So psi I is a vector valued function, and this denotes the usual Euclidean inner product in Rn. So the point of this, all of this, is that the singularity of u is at the fixed set S. It's hard to do the analysis if we're trying to compare things where we're moving the singularity around. So we've introduced these diffeomorphisms to keep the singularity along this fixed set. So this condition we wrote down on psi about the normal derivative, just means that that we keep the metric g standard in the normal direction, because the derivatives of u vanish on S, and then this psi I psi j term will be equal to the standard metric in the normal direction. So what we've achieved is to write down our problem in terms of an explicit differential operator involving the psi and this function f. And it's maybe easier to think of it factored into two ways. One is we can think of this thing for any metric g, and then we have the metric g actually depends upon the psi and u. So the derivative of f with respect to f, this is just the standard thing, as more or less the same as we encountered before, with the tiny difference that we're not projecting exactly to the normal direction near sigma, but to this, as it were, fixed direction. But in any case, this will be some second order operator whose leading term will be the Laplacian. The derivative with respect to psi is a less familiar thing. So if we differentiate, the derivative of a diffeomorphism is given by a vector field. So if we have such a vector field, v tilde, so this will be some compactly supported vector field, then the derivative, we're writing as p, it works out if you just from the sort of, from the way we set things up, one arrives at the following formula, that the derivative is given by differentiating the value of f that we have, the f that we have along v, and then subtracting off the linearized operator applied to the derivative of u along this vector field v. So that gives our sort of setup, but we haven't said anything about what kind of functions and so forth exactly we want to use. So now we go to that. So the sort of foundation for the analysis is to think about the flat model, which is just taking the Laplace operator on Rn, but we'll think about it as C star times Rn minus 2, but acting not on functions, but on sections of our standard line bundle with holonomy minus 1 going around the origin times Rn minus 2. So you can write down the Green's function, which inverts this Laplace operator using traditional techniques. One can write down a formula involving Bessel functions, for example, and understand the asymptotics of this thing. The crucial but completely elementary thing is that this Green's operator has homogeneity of the usual kind with respect to scaling. So that means that one only has to understand asymptotics in maybe 3 different regimes to understand the behavior of this Green's function over all values of x and y, roughly speaking. So more or less has a complete understanding of this Green's function. So we're going to work in Hölder spaces, variants of those. So we'll fix an exponent alpha, which is going to be between 0 and 1. It would be nice in many ways to take alpha equal to 1/2, but for some purposes that doesn't exactly work. So you can think of alpha as being a tiny bit less than 1/2, if you like. So in this situation, because of the non-trivial holonomy, sections that we're going to consider are forced to vanish at the origin. So if a function is in C alpha, that implies also a growth bound, but the size of the function is order r to the alpha, where r is the usual distance in the C coordinate. So if we take some rho in, we'll take it in C alpha, then we can solve, so let's see. So I'm not being completely precise in everything I'm going to write. In the end, we're only interested in compact subsets. We're working in this non-compact space. In the end, we only compare about compact subsets. So we can take our rho, for example, to be compactly supported, and then we are only interested in the estimates that we get over compact sets. But I won't say that explicitly. So if we take a rho in C alpha, then we can solve the equation delta F equals rho using its Green's operator, and you find that F has got an asymptotic expansion of the kind we've discussed. We're just involving two terms. So A rho and B rho are functions on Rn minus 2. And by doing sort of fairly straightforward estimates of these integrals, we get some Hölder bounds on A rho and B rho. So B rho is continuous. It's not quite differentiable because we can't quite take, so alpha plus a half is morally 1, but it should be roughly C1, but we're not quite there. So B is a bit less than being a differentiable function. A is a bit less than being a twice differentiable function. So now we'll extend our C alpha to a whole scale of a whole sequence of spaces that I call dk. So dk is defined by, we're looking at the rows where d rho is in C alpha, I forgot the comma there. For differential operators d of order up to k, but we're not allowed to take all k derivatives. We're allowed to take what are called k tangential vector fields, vector fields on Rn which are tangent to the singular set. So we can take any derivative in the Rn minus 2 direction. That's controlled in C alpha, or k. You can take k derivatives in the Rn minus 2 direction, or we could take d by d theta, or we could take r d by dr, but we're not allowed to take d by dr. So we don't control the kth derivative in the r direction of rho, but only r to the k times the kth derivative in the r direction. So the fact that you have to do that is a feature of this sort of situation, because if we're working with functions like r to the half or so on, then if you take enough derivatives in the r direction, they will become singular. So you can't hope to be able to control all the derivatives in the r direction. So similarly, we define another sequence, which is we call E, which is precisely set up so that the Laplacian of a section in a function in ek plus 2 lies in dk. So our previous result says that we have our map E, which takes A, which takes, well, the previous result said if we take A maps E2 to C1 alpha plus a half, but because in our space D we control all the derivatives in the Rn minus 2 direction, we can more or less just, by applying this to derivatives, we get corresponding estimates on all these ek spaces. Now we'll write E0 for the kernel of A in these E spaces. So then we get Frechet spaces, the intersection of all the E0Ks and the intersection of all the DKs. And these give a good setting for the analysis of our nonlinear PDE. That's to say, if our function u lies in ek plus 2, 0, then we find that both the Laplacian of u and also this quadratic expression, or cubic expression, we should say, involving the second and first derivative of u lie in dk. Remember, we were saying that this is the sort of essential part of the nonlinearity in the PDE we're discussing. So similarly, the whole, yeah, so this is the model thing. So how does that work? So when we're we're in the kernel of A, that means that U essentially behaves like r to the 3 over 2. So its second derivative, the worst thing is in the r direction, where it blows up like r to the minus a half. So roughly speaking, Uij is like r to the minus a half. On the hand, for the same reason, the derivatives Ui, Uj are like r to the half. So the whole thing behaves, roughly speaking, like r to the half, which, roughly speaking, is what it means to lie in this space, D, this space. So we'll also need some estimates in some other spaces. So if supposing rho, we don't suppose that rho is in C alpha, but only r times rho is in C alpha. So this would allow rho which behave like r to the minus a half, for example, suitable kind of. Then the estimates show that A rho is still defined and lies in a slightly weaker space, but now B rho wouldn't be defined. We wouldn't, if we had such a thing, then we applied the solution of delta U equal to rho wouldn't have a well-defined second term in its expansion. So we can define similar function spaces on our manifold, and we set up our problem as our differential operator from a set U mapping into the version of this D infinity, where U is contained in this product. We have the U and psi. U lies in the space defined by the script E's, and psi is to C infinity diffeomorphism. Actually, this is not quite precise because we have some, psi is a diffeomorphism and also satisfies this constraint on its normal derivative. So it's slightly imprecise. We're not really working inside the whole space of C infinity functions, but it's that's quite standard to represent the psi's we want to consider as an appropriate kind of space. The point is we use the C infinity norms to define the topology of the psi's. So all we have to do is to check that this map F fits into the framework where we can apply our Nash-Moser theory. In other words, if we deform our flat bundle, then we can do this whole lot of constructions in a family to represent things by a family of maps Ft of the kind we considered before, and then our general result will give us just what we needed. So we won't go through all of it. There are various things to check. I didn't write down all the hypotheses that one needs in this Nash-Moser theory. So there are various things to do. But let's just discuss the maybe the central thing, which is the inverting the linearized operator. So remember, the linearized operator is given by this thing P applied to a vector field, and our ordinary linearized operator L applied to F. So we want to solve this equation for an arbitrary rho in our space D infinity. But we want F to have the condition, this should lie inside our E0, so we want the order r to the 1/2 term, which I'll write A of F, should vanish. So before we were discussing the sort of flat model operator, the Laplacian. L is some more general kind of Laplace type operator. But following standard lines, one can show that the same analysis for the flat model more or less applies to L. And so one can solve the equation LG equals rho in a good way inside our spaces, but typically G will not have this leading term vanishing. Typically G will go like r to the 1/2 along sigma. So we need to do more. and this is where the v tilde comes in. Remember, we have this formula for the linearization of the action of v tilde. So if we substitute that into our, using the fact that this linearized operator appears here, we can write our equation in the following way. This left-hand side is given by applying our Green's operator, the inverse of L, to the derivative along v tilde of f. Of course, the v tilde is at present unknown, so this is a formula involving f we want to find and v tilde on both sides. But the condition we need is that this leading term a of f equals 0, so that gives the following condition. Now, this diffeomorphism psi that we're considering is not really completely invariant information. The invariant information is only really the image of our surface sigma, or maybe S, we should say, under psi. So the crucial part of v tilde is just the normal component of v tilde on sigma, which tells us infinitesimally how sigma moves. So let's write that normal component as v. So v is a section of the normal bundle of sigma. So the crucial thing, but completely essentially elementary, is that the term involving the leading, if we differentiate our solution, our object we have, u, along v tilde, and then we take the r to the half term, that's just given by the second term, the r to the 3 over term v, multiplied by this normal vector v. So say, remember that v is a section of the normal bundle to the minus 3 over 2. V is a section of the normal bundle. So these are thought of as complex line bundles. So we have a multiplication map that takes this to normal bundle to the minus 1/2, which is where A lives. So all this is, essentially, is just the formula that if we differentiate z to the 3 over 2, which remember is the r to the 3 over 2 term, then we get 3 over 2 times z to the half. But our hypothesis, remember, is that b is nowhere 0. So we can invert this algebraic operator b, and we can write the equation in this way. So essentially, v is given by this factor, all this stuff here. Now, if we take any normal vector field v, then we can choose an extension v tilde of it to a vector field over a neighborhood of our submanifold in a standard way of compact support. And so we're thinking of v tilde as determined by v, and so this whole thing is an equation for v. This doesn't depend upon v, this depends just on the row that we had, so this whole thing is an equation for v. So let's just look at it. So that this involves, we take the derivative of f, so the error term, what we had, then we apply the Green's operator, and then we take the leading term of that. So this f, remember, that lies in this space, this D space. So f is essentially things of order r to the half. So when I differentiate, I will get things essentially of order, speaking, r to the minus a half. So This one will not lie in our space C alpha, but it will lie in this weighted version r to the -1 C alpha that we mentioned before. So we can apply our estimates to get an estimate for this thing in terms of the norm of f in one of our suitable norms and a suitable norm of v. So remember, we can work arbitrarily close to our original solution, so we can suppose that f is arbitrarily small, and that means that we can, there's a unique solution to this equation if we make that assumption. And then we can go backwards to define f. So this is a proof that if we make a sufficiently small deformation from our original solution, the linearization is invertible. So that concludes our discussion of the proof. Okay, so let's just have a quick pause. So we've got 10 minutes to go on to our final section. Actually, it should have been called section 4. So remember, this is more context and remarks of various kind, general propaganda for why these kind of singular objects should be interesting. And it consists of 5 parts. Maybe we'll see how we get on. So we should emphasize first that studying this deformation problem is just the easiest thing of what one would really like to do. What we really like, for example, is to understand convergence properties of these things. If we have a sequence of these branched maximal sections, these singular sets, what can we say about a limit? Or the same goes for the other kind of problem involving these linear equations. So there's a whole world there to be explored. One result in this direction is of Zhang, who showed that in this more linear setup, if we take some a priori very general notion of a singular set, then in fact those sets are rectifiable, that's good news for people who the notion from the geometric measure theory. They're not too badly behaved. So to give some kind of context, the questions we're discussing involving these codimension 2 sets are, as we mentioned, they're analogous to free boundary problems, and the regularity theory for free boundary problems is a difficult topic. I shouldn't give the impression that it's a topic I know anything about, but I know it's difficult. And this, one of the main achievements of the Fields medalist Figali, the last Fields medalist, was involving results about this kind of regularity theory. We mentioned some ways in which these kind of questions interact with special holonomy via studying these kind of adiabatic limits for the spaces. There's another way, which involving gauge theory. So this story begins a few years ago with work of Taubes, who found that these kind of multi-valued objects, one-forms and spinors with branch sets, arise naturally from limits of solutions of various coupled type of equations on 3 manifolds and 4 manifolds. So coupled equations involving connections and some sort of additional fields. So one class called generalized Seiberg-Witten equations. Then there's a program of Hades and Walpuski, we discussed many times in our collaboration, to use a count of these kind of solutions of these kind of generalized Seiberg-Witten equations over 3 manifolds and 4 manifolds to give a counter term to get over the compactness difficulties involving enumerative theories for Yang-Mills instantons on G2 and spin 7 manifolds. Though it seems likely that there are what might call stable solutions to the G2 and spin 7 instanton equations with codimension 6 singularities. So I'm going to come back to this. Well, maybe there won't be time. There's work of Yankee Wang about this that I will maybe get to talk about more in the last section here, but maybe not. So it also seems likely, but a lot of work to do to prove, that these such codimension 2 singularities in the higher dimensional, in dimension 6, 7 and 8, should be related to the kind of codimension 2 singularities studied by Taubes and others, where one considers, as it were, instanton bubbling over codimension 4 submanifolds, or in the reverse direction, following very old work of Taubes in the 4-dimensional case, and Walpusky, then one can construct these G2 instantons, spin 7 instantons, by gluing in 4-dimensional instantons transverse to a calibrated submanifold, roughly speaking. So one could imagine that there will be some version of that involving solutions with these higher codimension singularities. There's also a discussion of this for the Hermitian Yang-Mills equations over Calabi-Yau threefolds, which interacts with algebraic geometry, because there one can express things in terms of stable holomorphic bundles. And there's some results of Alexander Doan about this kind of thing, relating point singularities on the data over curves, in that case, with reflexive sheaves over threefolds, and also other work of Yang Li describing a sort of a metric picture of this procedure. So another aspect is that these branch solutions probably can model sequences of calibrated submanifold collapsing to multiple covers. So this is something which is very familiar, I think, and much studied in Gromov-Witten theory and so on. In the case of complex curves, that you have to consider, you have to take account of the fact that you might have a map of a Riemann surface into your Calabi-Yau threefold, so which maps as a branched cover onto its image. And then you can imagine deforming this into a family of embeddings which converge to this branched cover. So it's natural to expect that these kind of branch solutions model the same kind of phenomena for other kinds of calibrated submanifolds, such as associative submanifolds, where there's some work of Alexander Doan and Walpusky about this in the unbranched case. There's also work in progress of Siki Hei studying this kind of phenomena for special Lagrangians. So there are, in other directions, will be my last thing, I think, there are parabolic versions of these things that we've discussed. So in the second case, we would consider taking a section which doesn't satisfy this what do you call it, maximal submanifold equation, but then evolve it by the bundle valued version of the mean curvature flow away from the singular set. But then we also move the singular set, in the same sense as we discussed before, to preserve this condition of the behavior around the singular set. So such a thing, if it could be set up, you'd expect this should be related to the G2 Laplacian flow on the 7 manifolds that were introduced by Robert Bryant, and similarly a 6-dimensional version of that. So this Nash-Moser theory has also often been applied to parabolic equations, and maybe one can use similar ideas to prove these short-term existence theorems for such equation. So even in the simplest situation, where we take a surface with a fixed Riemannian metric, we consider a configuration of points and a section of a bundle, a flat bundle, which evolves according just to the ordinary heat equation away from these points, but then these points have to move around to preserve the asymptotic condition that we're considering. That seems like an interesting kind of problem to explore. I could imagine that these points will collide. That will be kind of singularity formation that could happen, and this would correspond in our Calabi in our six-manifold picture to the six-manifold developing singularities when a three-sphere shrinks to a point in the familiar kind of way. But whether this indeed happens, whether it happens at finite time or at infinite time, or those are all interesting questions that one might explore. So my time is up. I won't get into part E, just to say it was discussing work of Yankee Wang on these singular G2 instantons, which he has a recent preprint about, and which he told us about in the September meeting. But I should finish there. So thank you for your attention. This is the last talk, so I think it's my present role to thank the organizers. So if everyone can unmute themselves, please. Let's thank the organizers, Simon and Sekuro and Dominic, for this organizing this workshop.
Well, we should also thank Simon for the set of two wonderful lectures. And if there are any further questions right now, you may want to raise your hand as we worked before, or I see Aaron, do you want to ask something? No? Okay, Greg, please. And then
yeah, I had a question about your context B in section 3 about the non-abelian, about the gauge theory type equations on 4 manifolds.
Yes. Mm-hmm.
Yes. So what kind of equations, could you say a little more, and what did you mean by generalized Seiberg-Witten equations? They can be generalized in many, many ways. So I was wondering what you had in mind.
Well, so Andre or Thomas would be better. I think.
What do you mean?
I think
abelian Seiberg-Witten equations?
Almost all of these equations, but I wouldn't.
Well, for example, I mean, one could add many monopole fields but keep a spin C connection, or one could make a non-abelian connection and couple that to section, and couple that to sections of some bundle in a general representation. So you might call those the non-abelian Seiberg-Witten equations. So does this theory apply to singular?
So it's really Andre and someone else should answer, but I think maybe in the simplest case would be to take our abelian connection, but take a number of spinor fields.
Right.
But I think the same. I think probably any of these equations, the same thing would apply to. But I haven't. It's not really kind of my particular thing. So other people would be able to answer better. But I think the same.
Would Vafa-Witten equations be part of the examples here?
Everyone?
Would Vafa-Witten equations be part of the examples?
Yes. Tubbs has a paper about that, in fact. He shows roughly that something along the lines that the only way a sequence of solutions to the Vafa-Witten equations can develop singularities is either the ordinary kind of instanton bubbling, or we get a codimension 2 singular set arising, and then you get this kind of monodromy going around the singular set, this kind of behavior for but it's not something that I have at the front of my mind right now, so that's really all I could say. But it will apply very generally, and that, in fact, that should possibly be related to. Let me think. That will very likely be related to this kind of, if we're considering sequences of co-associative submanifolds in a G2 manifold, then that should have some relation with the same kind of singular set. Possible that picture I would have.
Thank you.
So we have lots of questions. People are lined up, but not so much time. So we'll see how things go. Song is the next one, and then Dominique. Please go ahead, Song.
Okay, thank you. So I have a few, two questions. So the first question is, to my understanding, the situation where the Nash-Moser implicit function theorem is needed is related to something like the diffeomorphism group action being not differentiable. Is that similar in your situation, or is there a different reason why you cannot use the Euro implicit function theorem?
Yes. It's certainly, it has to do with the interaction between the smoothness of our diffeomorphism, or essentially this vector field in the linear, and the smoothness of the function, as it were, part. And if you write down the smoothness you need, you find, at least in the way that I see things, you find that you lose one derivative. Yeah, I'm not quite sure whether that can be seen exactly in the way you say about the actions, but very likely that would be a good way of thinking of it. Yeah,
I see. Okay, thanks. And another question is, you mentioned about this compactness problem for these maximal sections.
Mm-hmm.
Do we know anything about this, or is it completely unknown?
Well, it would be probably best safest to say no. If the equations are very well behaved away from the singular set, so if you had a sequence and you knew that the singular sets behaved well, then quite likely one could prove some good convergence result. But yeah, understanding the behavior of limits of these singular sets is beyond anything I've tried to do at the moment. It might be, when one goes to these questions, it may be just going back to the lower dimensional case of points in surfaces. That might be the best route, because many of the questions that one asks are still things that one doesn't know there. And obviously, understanding sets of points is a lot easier than understanding the general codimension 2 submanifold.
But this section do induce a Riemannian metric on the manifold, on the 3 manifold itself.
That's right, but it is slightly singular along the induced metric has got a mild singularity along the submanifold. So the curvature is in, I forget now, the curvature goes like maybe 1 over, yeah, I'd have to, maybe it goes like 1 over r. I think the curvature goes like 1 over r as you approach.
And
so
the Ricci curvature is still...
The Ricci curvature is positive, yes, so that it has, the signs work well, so you get good control of the Ricci curvature of the induced metric on M. Yeah.
Okay, thanks.
Okay, Dominique, please.
I wanted to ask more or less the same thing that Song asked, actually. So is it necessary to use Fréchet things in Nash-Moser, or could you do a more simplistic approach in a single Banach space, do you think?
Well, I don't think so. I mean, I spent about 2 years trying to do that, trying to control these derivatives, and then decided, let's do some smoothing. And then I decided, oh, maybe that's what Nash-Moser. So, but I don't. But it could be I was doing it in not a good way. So I can't. If we look at the work of Takahashi, for example, that doesn't, as far as I see, involve any smoothing. But I don't. Yeah, I don't see how to do it myself, shall we say? But you can't say it's impossible. But when I see it, one naturally seems to be losing. Anyway, seems to lose derivatives.
Okay. So
can I also ask a question?
who is that? Because the other, yeah.
I'm sorry.
Yeah, because I'm sorry, unless it's really directly connected to that, because otherwise there are it's really long.
No, it's not so connected. It's not so connected.
Okay, and we can postpone some of that for the discussion session. And let me give Rodrigo a chance to ask a question, please. Rodrigo?
Oh, thank you. Hi, Simon. I just wanted to ask, in the case where the harmonic section comes from co-associative fibration by hyperkähler manifolds. So if your hyperkähler manifold is an ALE space, you would have the situation where the intersection forms positive definites. So would this Nash-Moser theory break down somehow? Would you have to do something else for that situation?
No, I mean
because you'd have minimal
for the analogous deformation theorem. Yeah, that could, but that in the paper I mentioned, they're already does the relevant deformation theorem in that case. So the same setup can be applied to that case.
Okay, but you mentioned that the minimal submanifolds would be unstable.
Maybe not for the other parts about going back to the 7 manifold. That may be different, but just for this deformation problem, that would be the same.
Thank you.
Okay, thanks. There were also Andrew, Naichka, would you like to ask a question? Or anyone else, because suddenly people decided not to have hands on anymore. Andrew?
If there's still time, sure.
Yes. I think, is it okay? I mean, also for the chair, let's go for another 5 minutes, and then there will be a recess for lunch, and we'll reconnect at 3 p.m. Eastern time. Go ahead.
So I just wanted to ask about your item C on your context list. I think it was item C. The part about constructing multi-coverings of calibrated cycles. Can you say anything more about that? Like in the case of, say, like you have a special Lagrangian inside of a Calabi-Yau threefold, and then you have some kind of like branched harmonic form or something. Can you use it to make a special Lagrangian covering?
Well, this is work of Sigi Hay, who I see is just here. It's a work in progress. I don't know how much she wants me to say, but anyway, but the general, but I mean, just the general picture would be that if you go back to thinking of it as one forms rather than functions. So your one form is what is it like? So your function is like r to the 3 over 2. So your one form is like r to the half, as it were. So we take the graph of that inside the cotangent bundle. That's something like the standard picture of a branch cover. In fact, if we do it in the complex case, we more or less get exactly the standard picture. And if we do it in the case when the manifold is 2-dimensional, so our set is just a set of points, then we're just doing more or less the standard picture of a double branch cover. So the idea is that so that we know that the linearization of the special Lagrangian equation is just the plus equation. So we have one of these harmonic functions with this behavior is a good candidate, at least say, to model the deformations of this special Lagrangian into a nearby double thing with multiplicity 2. But of course, in a similar vein, at least to what I was saying, there's a lot of analysis required to prove something like that. This is similarly for all these kind of calibrated submanifolds, the deformation theory is given by solutions of some linear equation. So if you want to study these covers, you ought to be studying these multiple, the same phenomena should hold when you, for any of these equations. But this is all more or less what one should do rather than anything that I actually have.
Thank you.
Okay. Any other urgent question for a minute or so? If not, we should really thank Simon for this wonderful set of lectures and continue discussion in the afternoon.
Thank you for your attention. Thanks.
And then we'll reconnect, as I said, at 3 p.m. Eastern time. Okay, thank you. Bye.
Bye for now. Yep.